Transformation means austenite will become what kind of product. That's all. But to explain it, we choose which steel is tectonic. So we need to choose A1 temperature obviously. Because above A1 austenite is stable, below A1 it is unstable. The moment it becomes unstable, it will transform to some other product. Let it be this is your A1 or AE1, whatever you can write. E means equilibrium now. And it is C curve basically. Okay, I am joining this one today. So this is one temperature, this is one temperature, this is one temperature. Okay, and this is nose. So this is one temperature. Okay, and also we can choose one more temperature here. We can choose this temperatures. Okay, and this one is you understood. This is the critical temperature. Critical temperature is the that temperature. If it goes beyond that, transformation will start. Whether you rise or whether you low, whatever you can do, transformation will happen. Right? That's why it is the critical temperature. Then we are coming down. This is the nose temperature. Nose temperature means at this temperature, overall transformation rate is maximum. I am writing otherwise you will follow it. Maximum overall transformation will happen, right? How you can justify? Just see the incubation period is very less. Anybody remember incubation period? Let me ask. Okay, can you tell me? Incubation period? Yeah. Not exactly nose point. Any you can check the start curve, right? You remember this one is and this one is or I mean you can do transformation, no? Transformation started, this was transformation finishing. Okay. And how it obtained, you remember? We need to choose one specific temperature and we are giving only time. That means suppose your steel is here, you bring it to this point and keep the steel in that condition and allow it to cool. So again you bring a steel from here to this temperature and allow it to cool. Similarly, you get lot of dots. When you join the dots, start dots and end dots, it becomes a line continuous, and this is called people call sigmoidal curve or C curve. Anyway. Right? Anyways, fine. You understood it up to this. So the C incubation period. Suppose I choose temperature of this one, TTT. This temperature. So what is the incubation period? Can you tell me? From starting time to this time is 0 time. 0 second, for example. Transformation didn't start at all right now. Still austenite is there, and austenite will start forming at this point. See, if you join this one, okay? Just I am drawing a projection here. So from this two, I need to draw a projection up to this. So this will become your incubation period for this temperature. Right. Similarly, you want to find out the incubation period at C, nose of the C. So this is the zero time, and you need to draw a projection. So this is the other time. So this time is your incubation period. Just see. And similarly, suppose I want to choose the temperature of here. Let it be. Okay, no, sorry, transformation is not here. Anyway, So I am choosing a temperature of this one. Let it be. Okay. C. Temperature below the nose. So incubation period will be just connect it here and draw a projection. So this is your incubation period. So what conclusion we are getting? That means incubation period is very less at the nose. Or in other way you can say transformation will start early at the nose. But transformation will be delayed. If you go temperature above the nose and below the nose also, transformation will be delayed. It will start late. Or transformation will not proceed. Basically people call incubation period is that period or that time interval when transformation will not proceed. Austenite is still stable up to that. Is it fine, or you can ask me, because this is very important, that's why I am discussing again. Interview they ask, draw the diagram and explain it. This is fine up to this, or any confusion here? It's fine. So now the question may be like this in exam. Why the incubation period is minimum at the nose but higher above the nose, also higher below the nose? This is the question. Again I am asking. The question is why incubation period is less or minimum at the nose temperature, but it is higher above the nose temperature and below the nose temperature. That is the simple question. Anybody remember? Can anybody justify? Okay, you two people only. 3, 4. Why the incubation period is higher above the nose temperature and below the nose temperature, but it is minimum at the nose temperature? Why? The hint is simply, if you want to do the transformation, basically transformation which involves diffusion mainly, like benite and perlite. Okay. See, benite is mixed, but still carbon is moving also, no? Okay. That's why it is forming carbides. When carbon moves, it becomes carbides, basically. Okay. Because in perlite, ferrite and carbide, no? So when carbon will move, it will concentrate and become Fe3C. Okay. Similarly, in benite also you have carbide and ferrite, same. Right? You need carbides, so carbon need to diffuse. So when there is a diffusion transformation, that means your transformation will be proceeded by nucleation and growth mechanism. If you want, you can write. If transformation happened by diffusion or diffusional transformation, whatever you can say. If transformation happened by diffusion, then it occurs by nucleation and growth. For example, let it be this is gamma, and it become unstable. It want to form now perlite, for example. So perlite nucleation will start. Small nuclei will form. Perlite nuclei will form. And you remember they form basically along the grain boundaries, obviously, or it will start from the grain boundary and goes inside later. So this is, for example, perlite maybe. And this small perlite nuclei will grow then. It will grow towards center. It will become bigger. This will also become bigger. This will also become bigger. This will also become bigger. So lot of big perlite will form. Now entire gamma become perlite. So this is the small nuclei will form. It will grow. So you have to always remember, whenever there is the transformation happening and by diffusion mechanism, then nucleation will start, then growth will happen. But if it is not diffusional, then it is diffusionless, only shear will happen, basically. Just your parent austenite in one particular plane, in the parent austenite, it will shear. Atoms will just move a little bit. But diffusion means atoms will move to a long distance, more than 1 atomic distance you can say. Okay. Up to this it is okay, right? So now okay, let's continue. Now there is two concepts. One is, see, I am justifying why I have less time period for what is that called? Yeah, I mean incubation period is less here. Why it is higher here? Why it is higher here? I want to justify that. So you can see diffusion occurs by nucleation and growth mechanisms. So that means you have one nucleation rate and growth rate is also there. Two concepts: nucleation rate. Because we are talking about kinetics now. Incubation period is less means your kinetics is high. Okay. Incubation period is more means your kinetics is slow. Incubation period is high means your kinetics is slow. Right? You got up to this point, huh? So nucleation rate and growth rate. In other words, I can say higher is the nucleation rate, faster is the kinetics. Higher is the growth rate, faster is the kinetics. But both mechanisms are different now. Both mechanisms are different. One is nucleation rate, one is growth rate. Condition maybe sometimes will be like this. Nucleation rate will be high, but growth rate will be slow. So overall transformation will be reduced. The condition may be like this. Growth rate will be high, nucleation rate will be slow. Then overall transformation will also get delayed, become slow. But when both are good, nucleation rate is also good, growth rate is also good. I mean nucleation rate is high, growth rate is high. The moment you combine, that is called overall transformation. That means if overall transformation is high, kinetics is fast. If overall transformation is slow, kinetics is slow, incubation period is more. Do you got up to this or shall I write? Okay. So nucleation rate I am writing N and growth rate I am writing G. So this product, nucleation rate into growth rate, will decide your overall kinetics or overall transformation. So your overall transformation depends upon nucleation rate multiplied with growth rate. So now how I justify it? Okay. Just see at the nodes this incubation period is less, that means kinetics is fast. Transformation will start early. Why? Because if you multiply the nucleation rate, growth rate, and at this point, most point, it is more. So I can write here as well. At this point, N into G is high. But if I consider the temperature of this one, this temperature, N into G will be less. I consider this temperature, N into G will be less. Now you got the point? Why? Because two factors are there. Nucleation rate is there, growth rate is there, right? So okay, fine. So it means at this point N into G is high. It means nucleation is also good, growth rate is also good. Why this is happening? Because temperature at this point temperature is also sufficient, and you have good undercooling also. See, this N is decided by undercooling. That means higher the undercooling, higher is the nucleation rate, you know. Similarly, undercooling means you understood now suppose from oxidizing temperature to that temperature, that gap, difference, that is called delta T. Difference in oxidizing temperature and your transformation temperature, that is delta T. So more you go down, delta T will be more, of course no, more you go down, delta T will be more. So more delta T means more undercooling, so more nucleation rate. Is it fine? That means this temperature, now you tell me, at this gap, for example, let it be, from this temperature to this temperature, what is the delta T? And from this temperature to this temperature, what is the delta T? This to this and this to this. Delta T is higher from this to this, of course. Yes. So that means nucleation rate is high, of course, because undercooling is high. But this to this undercooling will be less. So undercooling will be less means in this condition your nucleation rate will be also less. So unless until nuclei will form, growth will never happen. First nuclei should form, that will grow. No? So since the undercooling is less at high temperature, you have less nucleation rate. So since the nucleation rate is less, so overall transformation will be also less because N is affected by undercooling. You got the point? This will be less now. But this is less means G will not start because nuclei is not forming. How growth will happen? Yes. You got the point? Same thing happens at C. From this temperature to this temperature. Sorry, this one. Let's see. This is all N into G. But the point is, this temperature to this temperature, undercooling is very high. But still overall transformation is less. Why? Because you have more undercooling. But temperature is very less. And diffusion need high temperature. Okay, diffusion need high temperature. But since that means growth rate will be affected, N is high, but G is less. Up to this you understood, right? Or shall I write on this one? Any confusion? No confusion. So that's why. So you can simply, otherwise in other words, you can simply write write one line or two lines. Nucleation rate is directly proportional to undercooling. Similarly, you can write growth rate is directly proportional to temperature. Or growth rate is also directly proportional to diffusion. These are the main points. I think up to this it is clear. Okay, fine. Okay, I forgot to represent the things here. It is austenite, you remember? This is also austenite. You can write unstable austenite, that is fine. But to justify, you can write unstable, no issue. So this is austenite, but this is unstable. Now transformation will start. So this is now, yeah, we will discuss about now the cooling curves. If the question will be like this, draw a TTT diagram and superimpose the cooling curve on this and tell us what kind of heat treatment process is that. Each cooling curve represents what kind of heat treatment. And each cooling curve gives what kind of product. These are the two questions. Again, I am saying you have one TTT diagram now. Just superimpose the cooling curve on this TTT diagram. The moment you superimpose cooling curves, right, you have to justify each cooling curve gives what kind of product after transformation, and each cooling curves will give you what kind of heat treatment, or it justifies what kind of heat treatment, because we can have many kind of heat treatment. We'll discuss that slowly, maybe after 2-3 class. So, okay, so I will start at this point. Okay, I will change the color. So one cooling curve will be like this. One cooling curve will be like this. So this is cooling curve 1, for example. This is cooling curve 2. One cooling curve will be like this. This is cooling curve 3. One cooling curve will be like this. This is C4, right? And one cooling curve will be like this. C5. So many cooling curves, it depends on, you can draw many cooling curves, no issue. Cooling curve means temperature versus time only. Now just see, very interesting point. We'll see first the heat treatment. I know you don't know anything about heat treatment right now, different heat treatment, but still just remember. So this heat treatment, this one, the first cooling curve and second cooling curve. This heat treatment is called hardening. The name of heat treatment is called hardening heat treatment. I am writing here C1 and C2 cooling curve. It shows which kind of heat treatment? Hardening. No, the technique is called called quenching, but I am talking about the heat treatment name or process. That is called hardening heat treatment. Hardening, you understood the name. That means material hardness will improve or material strength will improve, right? Similarly now, see, cooling curve 3. Cooling curve 3, there is, you can say, there is, what I can say. Okay, you can say like this. You cannot give any specific name to this anyway, but you can give specific name to C4 and C5. C4 and C5. C4 and C5. So C4 and C5. So C4. Just see which one is higher cooling rate, C4 or C5? C4 have higher cooling rate, faster cooling because time gap is there. Right? But your time required is more for cooling. So C4 is actually called normalizing. Normalizing means it is basically air cooling. You are doing cooling in the air. Just take out the sample and put it in air. It will cool. Or some people do what? They allow the fan to cool it somewhat faster. Put it under a fan, right? And C5 is annealing. So normalizing heat treatment, annealing heat treatment, and hardening heat. These are the major heat treatments. We'll discuss that one by one. Okay. So that means what I can say, which one will be furnace cool? So this is
annealing.
Annealing is very slow cooling, so it is furnace cooling. Furnace cooling means what? You put the sample in the furnace first, you switch on the furnace will rise the temperature, the sample temperature will go to the oxidizing temperature, you hold it, after holding you need to cool it, you just switch off the furnace. Don't take out the sample. But the moment you take out the sample, that becomes normalizing. Is it okay? And hardening means you take out the sample and put it into water directly, or put it into ice bath, or put it into brine solution, means salt solution, or you can put it into the oil very fast, right? I think this is fine now. Now we'll discuss about the products. See, this is the main important part, because if you, I don't know, you are doing any NPTEL courses by yourself, or you are not interested. Okay, class teaching is very sufficient for you maybe. Okay, anyways, fine. NPTEL course. If you go through the NPTEL course, actually I appeared that course actually once upon a time. So they ask this kind of question. They will give you different cooling curves, and they will ask what kind of product it will form. This is the question. So now see, C1 and C2 are hardening, and these are rapid cooling, very fast cooling. So you will end up with Martensite. So product I can write C1 and C2 cooling curve will give you Martensite. But there is a glitch here. There is a glitch. See, suppose your cooling curve is, okay, let me change the color. Okay, I can draw another cooling curve. Suppose your cooling curve is like this, but it is up to this. This is MS, this is MF. Your cooling curve is up to this. This is your cooling. So what will happen?
Retained austenite.
You will end up with Martensite plus retained austenite. Okay, so don't get confused. So C1, C2 is giving Martensite. Suppose this is maybe
C6.
C7. So C7 will give you Martensite plus retained austenite. Okay. Similarly, suppose now the cooling, just now tell me C1 will give you 100% Martensite. You understood why? Because this cooling curve has crossed Martensite start and also crossed the Martensite finish. That's why. So people call Martensite is a air thermal transformation. The same question was asked to Manila ma'am during the interview. Recently she faced also interview for promotion. So they asked this question. So what is the meaning of air thermal transformation? I don't know she able to answer it or not, but she told me that they asked me this question. So A thermal transformation means, I told you, Martin-Sided transformation is diffusionless, shear transformation, it is also athermal. Athermal transformation means it doesn't depend upon the time, it will only depend upon temperature. Let me clarify this. For example, you are cooling very fast, rapid cooling, but you stop here. Listen carefully, you are cooling very fast, but you are stopping here. So do you think that you will get Martin-Side? You will never get Martin-Side. You are cooling at a very fast, but you are not crossing the MS and MF. Transformation of Martin-Side will never start. That is called athermal. Similarly, you are cooling and you are reaching to this point again. No Martin-Side. So Martin-Side transformation will start unless until you cross the MS, and it will finish if you cross the MF. And that MS and MF will be affected by alloying elements. That is next lecture. We'll discuss that, all the things. Okay, you got the point? So the athermal transformation means it only depends upon the temperature. It doesn't affected by time. You can cool very fast, no issue. But you will never get Martin-Side unless until you cross the MS or you cross the MS. Is it okay till now? Okay, so now we'll talk about, this point, this is very interesting, C3. You remember, there can be a line at the middle of this two curve. And this middle of two curve, okay, let me ask you a question. I don't know your name, okay, anyway. Can you tell me that middle of the C curve showing what exactly? First curve is transformation start, last one is transformation end or finish. Middle one? Very good, very good. So this middle curve shows 50% transformation curve. 50% transformation means austenite has transformed 50% amount. Rest 50% austenite will remain, or if you allow the time or if you allow the temperature, it can transform. Depends. No? Okay, so you understood? Now see the curve. This curve has come and finally crossed this one and it is moving down. So that means since this curve has crossed first, so transformation has started. It will go on. It will cross the 50% now. It may be somewhat 60 or maybe 70. So 70% transformation has happened, and rest you can see it crossed the MS, it crossed the MF also. So that means suppose 60 to 70% transformation has happened for austenite to your perlite maybe. I will discuss that. Perlite, actually perlite. And rest 40% or 30% will transform into Martin-Side. You got the point now? But just if it will cross the 50%, only 50%. Then 50% your perlite and 50% Martin-Side. But another question, suppose this curve will come and stop here. Then you have three phases again, three phases. One is perlite, one is Martin-Side, and one is retained austenite. Do you got the point or any confusion? Shall I tell again? You need to check the points, temperature and time. Okay, fine. So finally this is completely touching the transformation start. So transformation will start, and again it crossed the 50%, again it crossed the 100%. So transformation will finish. Whatever austenite you have, it will transform into one phase. That is actually perlite, mixture of phases. Okay. So finally you are getting mixture of phases. But you are crossing MF also. But already transformation is complete. All the austenite become perlite. So there will be no retained austenite to get transformed into Martin-Side. Do you got the point? So this point C4 will give you perlite. Then 100% perlite. Because it is eutectoid still, that's why. If it is hypo, then things will change. You have provided tetrahedral ferrite also. Okay, anyway. So similarly C5, take care of it. 100% perlite. C5 is. So I think cooling curves you understood, and the heat treatment, different heat treatments you understood, and now the products also you understood. So you may get similar question completely in exam. But cooling curves may be something different, but you can get this question. You have any doubt, you can ask me right now. No, Jomini quenching actually that talks about hardenability. Hardenability means where the cooling rate is very high, Martin-Side will form. When the cooling rate will be slow, perlite and ferrite will form, and cooling rate will be very slow, then and the kind of phase will form. No, benite will not form. Benite will, okay, I'll discuss that. Yeah, that is the main question you asked. Okay, let me clarify here. Which color I will use? This suggestion.
Pink.
Pink. Okay, so your starting temperature is this. Now your cooling curve is like this, for example. You are cooling and you are stopping here, and the cooling curve goes like this. Let it be maybe your C8. See, I started from austenitizing temperature. I brought it quickly to this temperature. That is kind of quenching kind of situation, very fast. But now isothermal cooling started. See, isothermal cooling means temperature is constant here, and you allow the time just it will slowly cool. You understood, or shall I repeat? You start at high temperature. See, these are continuous cooling curves. C1, C2, C4, C5, C7, C8 also, C7. All these cooling curves are continuous, but this is not continuous. You are continuously cooling to up to this, but then again you are holding here. So holding means transformation will depend upon this temperature only. Okay, of course this temperature. That means it needs more time because incubation period is more. So at the end you will end up with benite. We discussed the three types of products: perlite, benite, and martensite. So you will end up with this one, Ca benite. So people called benite formation happens due to isothermal cooling. So first stage is quenching, but you need to hold at benite transformation temperature, then only. That is the condition. Because if you remember, we have discussed about now what is the range of formation of different products. Perlite range is how much? Anybody remember? 727 to 550. Very good. That means just below 550 your benite transformation will start, but it will go up to 250. That is the range. If you go below that, martensite will form. So now my question is, why martensites will start forming below 220, not around 550 or 350? No, don't. I'm asking like it. Why martensite will form below 210 or 210? It will start at 210, not above that. We already discussed that soon. I remember. Yeah, can you tell me? Yeah, so can you tell me? Why martensite will form below 210? It is not forming above 210. That is the vague answer. Okay, suppose there is no diagram like this, then how will decide? There is no TTT diagram. How will decide then? Because martensite transformation is diffusion-less. Diffusion-less means diffusion is not happening at all. Because temperature is so low. Neither iron atom will move, carbon atom also cannot move. Because carbon atoms start diffusing above 200 basically, but it is slow. But if you go above, then it will become higher somehow. But austenite cannot remain stable also, no? That is the point. Austenite is unstable now. It has to transform to another product. So it will shear up and give you martensite. So you can write martensite will start forming below 220 or 210 because at that temperature is so low that diffusion do not occur at all. No migration of atoms will occur, neither carbon nor iron. But that austenite is unstable. It has to transform. So it will transform into shear transformation and it will give you martensite. That is the answer. Okay, you understood benite now? And if you remember, we have two types of benite, upper and lower. So you have to see again at what temperature you are holding. Suppose I will stop here. Can you tell me which kind of benite will form? And if I will stop here, for example, this temperature, lower benite, very good. And if there is a question, which one is which benite will give you better property? Suppose you have same kind of steel, same composition, okay, everything is same, but you have one upper and one lower benite. So which steel you are going to use for application? Lower benite, very good. Lower benite, why? Because lower benite is very, very tough. Toughness means ductility is also good, strength is also good. Both properties are there. China, you know, I told you the example. Huh? China, the railway tracks of China are benitic steel, but still we are using perlite right now also. We have run the Vande Bharat, but I don't know. Anyway, but still we are using perlite steel. Maybe suppose we want, like in Japan they have a very good train, you know, bullet train. But China, I don't know exactly, but I have seen the news that China is now running a train which is traveling at 1,000 km/h something maybe around. I'm not sure, but just state it. No? I have watched it from social media, so I'm not sure about that. Anyways, so if you need, suppose you want a railway track to run very high-speed train, you need benitic steel, otherwise it will fail. Okay. So that means comparison between perlite and benite is better, of course. It is more tougher. Why? Why can you think of it? Because in perlite you have lot of carbides also, no? You have lot of carbides. In benite you have carbide and ferrite, same thing, both are similar, but structure is different, morphology is different. Anybody remember what is the structure of benite upper and lower? See, you cannot observe the benite using optical microscope properly. Properly you cannot observe it because they are very small size. If the size of the particles or if the size of the grains are very, very small, you cannot able to resolve it. You remember I told you resolution and magnification. You can magnify it, but you cannot resolve it because they are so close to one another. How you can distinguish which one is exactly benite and all? You cannot. So you are using what? Transmission electron microscope. So if you see the benite in transmission electron microscope, you will end up with like this cartoon diagram in front. So they have ferrite plate like this. These are plate of ferrite. Somebody is waiting. And you have carbide source. Which one is ferrite and which one is carbide? So this is carbide and this is ferrite. Or this is alpha, this is alpha, this is alpha. Sandwich kind of structure, see? Kind of sandwich. You have plates of ferrite and in between plates of ferrite you have cementite precipitated. And another kind of benite will be like this. Your ferrite plate will be there, of course. Okay. Pink color. What are these? What are these? These are discontinuous carbides. So these are discontinuous carbides. And these are alpha. And little amount of carbide also precipitate, very less actually. Now just tell me which one will give you better toughness. Just see. Discontinuous one, very good. Because if a crack will initiate in the carbide, it will stop by the ferrite matrix. The ferrite matrix is ductile, so it will stop. Because it will deform. Instead of breakdown, the crack will blunt actually. Technically it is called blunting of crack. If the crack tip is sharp, the crack can easily propagate. But if the crack will be bent like this, then it cannot decide where it will move. So it will stop. Why crack will start from the cementite? Carbides? Because it is a brittle phase. No, it is a brittle. But ferrite is very soft. So because of these two kind of things, brittle phase plus soft phase, it will give you good toughness. Fine. Now you need to check which one is upper and which one is lower. That is your assignment. Just see. And you can see those discontinuous carbides are in an angle, not perpendicular. In an angle, 60 degree, people call. basically. That is 60-degree bend, somewhat. Okay, I will share the video otherwise. I have a very good video on this. I'll share it. You'll see the different morphology, different heat treatments. Okay. Fine. Any questions? See, if you have any doubt, just clarify it on the same day better. You come to me and ask. Don't get scared. I will clear it.